inside. Inside. Put up, down. So. You're okay there. Just hang on to it. Hang on to it. All right, let's hit this lap. Hit this lap. 3, 2, 1. All clear out. All clear out. Reset your tools. Let's finish this off. Great job so far. One more. Bring it on, buddy. Nice job. Flag, and that is one hell of a drive. Nice job, buddy. Well done. Nice job today. That was a hell of a drive.
Hello, everyone. I'm Christopher Savoie. I'm the CEO and co-founder of Zapata Computing. I'm here with Mark Jack, who's the quantum application scientist at Zapata Computing, Eric Bretzman, who's technical director at Andretti Autosport, and with Nick Heinz, who's senior vehicle dynamics engineer, also at Andretti Autosport. Next slide. So we are here to talk about the work that we're doing together with Andretti Autosport. And racing is kind of cool. It's cool to talk about, but I think the main takeaway that we would really like to talk about, most of you are probably not race car drivers or race car teams or involved in that, is really the analogy that this gives to other areas and how applicable some of the work that we're doing on some pretty deep analytics in physical models and machine learning on some very real data sets that have some real live consequences, and they're really fast every week that we're working on this stuff, and how that might actually be applicable to other areas, other industrial areas, other areas of impact and importance. And this is really where it happens every week. That's the Racing Analytics Control Center. We call it the rack or the truck, but in this vehicle, we have actually all the analytics and computation that from the data, like 1,000 different sensors on each of these cars. We have 6 cars running every week that we take the data down and we're doing analytics for. So we're doing all the model building and analytics, and the drivers are also in there with us every week talking about the data more than anything. You know, one of the impressions I got when I brought my son there is like, well, this isn't really just a driving competition. This is really an engineering competition. I'd really like to kind of impress that on you, that the data that we're doing in here is at a rate and pace and size that is pretty incomparable and very relevant to a lot of other industrial applications. Next, and to talk more about what we actually do in that center, I'll pass it over to Eric.
Thanks, Christopher. Yeah, we're often asked what exactly it is we do in the rack at the racetrack, and then the rest of the time it's a year-round thing for us, huge team of engineers. And our engineers are leveraging the existing data we have to build advanced machine learning models on some of our key cases. We're starting with models with classic computing. We'll soon be implementing some quantum-inspired algorithms, and in the future we'll be ready and expect to use quantum computers where we can find an advantage. We've identified some cases with Zapata and our engineers, and with the help of Zapata and the Orchestra platform, we're working towards having a competitive advantage in our sport now. And 3 of the key areas that we're going to talk about today are tire modeling, tire degradation, race strategy, and predictive yellow flag modeling. Those are all hugely impactful to what we do every weekend. And Nick and Mark are here to tell you more about that in detail and how that applies to industries outside of racing.
Yeah, so thanks, Eric. So one of the main aspects that we look at over the course of a race weekend is tire degradation. So as several times over the race, we have to swap out tires because as you wear the tire, as you use them, the tire's performance obviously degrades. So push too far on a set of tires, and you run the risk of falling out of the race. So building these tire degradation models is actually pretty complex and relies on a couple of different factors, namely ambient conditions, the tire compound construction, the track surface roughness, and also how hard the driver is pushing on them. So because of this inherent complexity, this is an excellent use case for machine learning techniques.
Yes, thank you, Nick. So we're working very closely with Andretti in terms of exploring and understanding this use case. So this is around predictive maintenance. So we see this as a high-speed use case for predictive maintenance. What are we dealing with here? Mostly kind of analyzing time series data, which we get from IndyCar directly. So this is somewhat different data than what Chris was mentioning earlier around vehicle simulations. And yeah, one of the core challenges here is figuring out how to process the data, doing the feature engineering. So there's new features which we need to generate, where we talk very closely with Nick and his colleagues around traffic density modeling, for example, which feeds into things like other models like overtake. And so how do you do that effectively? All the data pre-processing, the feature generation, and then the feature selection, feature reduction step. There, I guess the core issue is to figure out what really matters, meaning, so that's where we kind of need to closely work with Nick, Olivier, and others on the Andretti teams to really understand what features do we need to select to do accurate machine learning models at the same time. So it's a balancing act of taking just the right amount of data. You cannot necessarily generalize across, different aspects like drivers, seasons, tracks. All of those are things we need to truly understand, and that's where kind of the true collaborative aspect comes into play, interacting with Nick, truly understanding what actually matters for this particular use case. And of course, it has applications in a whole bunch of other industries: logistics, supply chain, manufacturing. Just think about, trying to detect cracks or other fissures, using image recognition, classification techniques. So a lot of these things are kind of directly applicable long-term to other industries. And on that note, we could switch to the next slide and next use case.
Yeah. So another primary use case for us is a race strategy. So what is race strategy, right? During the race, we have several decisions that we have to make. We're accounting for fuel management, pit stop selection, also when we're going to change tires and what compound we're going to change to. So we have several choices. So this results in basically a large combinatorial optimization problem. So how do we go about solving that?
So as Nick said, it's a huge optimization problem, which, again, what's the applicability to your industry? Think of any industry, optimization. You'll find some optimization use case to solve. In the financial industry, for example, we actually have some in-house expertise doing portfolio optimization using one of our kind of core technologies which we've developed, which is essentially going to lead us into possible also quantum-inspired, quantum-enhanced algorithm development in this context. And so race strategy, there again, the core issue there in optimization is how do you do this fast and effective, and this is probably one of the use cases where we're going to first be able to explore how to do this, maybe accelerate it using kind of quantum-inspired or quantum-enhanced ideas. And so on that note, we'd like to move on to the third and last use case, the yellow flags.
Yeah, so yellow flags come out whenever there's an on-track incident. You can't really ever know when they're going to come out. You just have to react to it. And unfortunately, they're hugely consequential to the race outcome. So typically when a yellow flag comes out for the leaders, it's going to cause a problem. But on the flip side, it can also be an opportunity for people further back in the race to move up. So while we can't exactly predict when these are going to come out, we can be prepared for when they do, and we can make a smart and strategic decision. So one of the ways we do this is by running through several race simulations where we go through an entire array of possible outcomes for the race so that when the yellow flag does come out, we're able to smartly make the right strategic decision.
So yellow flags are one of these kind of key additional aspects, especially in the IndyCar setting, that requires us to kind of think outside of the box of just machine learning and optimization. So this leads into this whole topic of synthetic data generation. How do you model these type of rare events, or how do you simulate them most effectively so you can train your machine learning models on that? So currently we're kind of going through the phase of actually having to build a race simulator to, as realistically as possible, try to emulate a race situation, kind of a synthetic race in which we can then train our machine learning models. And again, this has all kinds of applications in other industries. Think about, for example, cyber threat detection, which I'm sure the federal government is very interested in, credit card fraud, fraud detection. So this has applications in all kinds of other arenas. So on that note, I'd like to pass it back to Christopher, who's going to talk about the quantum aspects.
Yeah, so we haven't spoken a lot about quantum. Here we are at a quantum conference, so I'm sure everyone in the audience is like, well, what does this matter? Why are we even talking about this kind of data analytics without mentioning quantum? But I hope for some of you who are at least familiar with the kind of questions mathematically that's behind the hood, under the hood here, sorry for the pun there, are directly applicable mathematically to some of the speedups that we hope we will get from quantum computers. So when we're doing optimization, simulation, and all of these things particularly, but on the shorter term, we are already finding in our work, and maybe you've seen some of our papers recently, that particularly in areas like enhanced machine learning and enhanced particularly generative modeling within that, that these things have, these concepts and capabilities actually have direct applicability to these kinds of data sets. So we have a lot of opportunities here that we're already looking at and we have the substrate of this data to actually expand actually implementing these mechanisms. Initially on classical hardware, we can use matrix product states, as some of you may know, to kind of simulate quantum statistics. But the statistical thing that quantum computers do can be directly applied to many of these problems and give us a near-term advantage, is what we're seeing. So this year, the first thing that we're going to do is get us up to the state-of-the-art in machine learning classically. This is the step we do with all of our customers, all of our partners, is you can't really compare, oh, do we have a quantum advantage? We think we might, let's start with quantum. No. The first step is getting to, with the data that you have, to the absolute state-of-the-art bleeding edge of what you can do classically. Everyone should start there. And that may be good enough to get some advantage. We already are finding that we're getting advantage, and that's going to help us win races. And from that point, you start enhancing with baby steps in quantum, baby steps that could be significant, 2%, 5% better. When you have the consequences here of one race after 500 miles at 200 some miles an hour, the difference in first and second, sometimes milliseconds, sometimes half a second over 500 miles. That's pretty incredible, the kind of thing we have to do here. And the modeling that we're doing, the physical modeling and all of the kind of modeling that we're doing and the mathematics that go into that is pretty incredible. And I encourage you to come talk to us at the booth and we can show you a little bit about that. But the point here is that we have the substrate. We're bringing this to the state of the art of classical machine learning and classical optimization. And then we're actually enhancing this with the quantum capabilities. And we're finding, at least on classical simulated hardware, some advantage that we believe that we're going to be able to start rolling out in the next year or two of racing. And we can talk a little bit about how this actually gets built in.
Yes, so thank you, Christopher. So where does quantum now fit into the stack? As you can see from the diagram, we're using both classical and quantum hardware. So our Orchestra platform is going to be what we're going to be using to be able to train and deploy, to kind of train initially our models. We need the cloud infrastructure to access the data. So we're using instances on Azure. Azure is kind of the preferred environment for Andretti because a lot of their kind of historic databases have already been built in Microsoft Azure. And so those trained models will then, we will then do inference on. The idea is to probably very likely have some hardware on the server hardware in the rack truck itself and we'll also need some edge hardware trackside to kind of do the live real-time prediction. So on that note, I'd like to move on to the next slide. And so this is kind of the tool on the software side that we as data scientists, machine learning engineers on the Zapata side actually use day by day, our Orchestra software. You see here kind of a snapshot of this nice kind of GUI-like interface. So we have a new product, Orchestra Studio, that allows us to work like with Jupyter Notebook style setting, building machine learning workflows, doing the whole data pre-processing pipelines, and also being able to show some visualizations and being able to communicate that then back to Eric and Nick and team on the Andretti side and getting their feedback in terms of the results we're finding and also how we basically present results, how we do the visualization. So there's a lot of communication on that note right now. And with that, I'd like to pass it back to Eric, who's going to talk about some of the plots they actually study.
Yeah, this is commonly how historically motorsports have looked at like a time chart of, in this case, this is a lateral and longitudinal body acceleration for a vehicle doing a lap around a track in Ohio. Our data is hooked directly into the work that Mark's team's done and Zapata's done with our data lake, and we have just a really tight loop with the Zapata group, and really, it's a direct connection, and it's really to the point where it can quickly impact our decisions on race day.
So what's next? 2023 season begins in March. We're taking the models that we've already built with the historical data and the data that we got from last year by working hand in hand in the rack and back in Indy and our headquarters together to build models. So we're going to be taking them and applying them. We're not going to say, okay, make this decision this year, but we're going to be able to compare how our decision would fare against a race engineer's decision on track day, and actually be informative starting this year. We will also be taking the quantum methods that we have that we can use to enhance the state-of-the-art machine learning methods that we're already going to be applying at the track and build these into our simulations, and hopefully towards the end of the year we'll be applying those as well and testing. This is an iterative process. It's an agile process that we have. It always is anyways, always has been, to get better and better at the models, better and better at visualizing the models, and really taking the diamonds in the rough out of there and using them. Our applications really will, we believe, already have some impact, and we're seeing data that is very useful. Particularly interested in some of the simulation enhancements that we can do, because you can only run so many laps around a track. You need to actually work hard to find the data that will inform your models better, and we already have some advantages in that area, and we're excited to actually put that in progress and win some races.